So everything I'm going to talk about is joint work with Carlos and Ron Levy. And starting point of what we did was the theorem of Dave Benson. Which I'm not going to state precisely right now, that'll come later. But basically what he said is that, what he showed is that for any finite group G, and prime T, one can give purely algebraic description, and that's where I'll be more precise later on, of the mod P homology of the loop space on BG, P completed. Okay. And so, first time I saw this, I found it very surprising, just because the definition of P completion, that's Gauss-Field-Kahn P completion, of course, definition is sufficiently complicated that I found it hard to imagine how it could all be distilled down into something purely algebraic. To make it slightly more precise in that he says it's the homology of a chain complex of projective FPG modules that satisfies a certain conditions. Okay. And then what we gradually realized by looking at it more closely is that it's really a statement about loop spaces on certain plus constructions, of which P completion in this situation is a very special case. So so this uses two properties of P completion of a space, and I'll state only when fundamental group of the space is connected, is finite. And okay, I didn't write it down, but understood here that X is connected. So first property is that pi 1 of P completion is pi 1 of X modulo the smallest normal subgroup of P power index. So and then the second property is that, and here, again, I'm not writing down details, but it's understood that this isomorphism is induced by the natural map from X to its P completion. And the same thing here, that pi 1, that homology of X And so, in fact, these two properties, they don't determine the p-completion of the homotopy type. It's easy to see that that's not the case. But they do determine, they are enough to determine the homology of its loop space. Okay, so more generally, first of all, a little terminology, because I mentioned plus constructions. That's plus constructions, of course, in the sense of equivalent, but in a slightly more general context. That so given connected space X and H normal imply 1 of X, normal subgroup, and a commutative ring R, we'll just say that plus construction for the triple. So that's a space map. I'll simplify the notation by leaving off the H, but well, such that first of all, that in pi 1, is onto with kernel H, and secondly, that it's an isomorphism write it this way. Isomorphism in homology with R coefficients, but one has to do it slightly more generally with arbitrary twist coefficients. So, and to, just as in Quillen's plus construction, and for all R, for every module over the group ring, so this would be pi 1 of for every such module. Okay, so in other words, well, and by the same proof, more generally than what Quillen did by it, but by exactly the same argument, this holds, or this exists, rather, whenever H is R perfect. Meaning that H lower 1 of H coefficients in R. And H's. So Quillen, of course, was looking at the case where R is the group of integers. So R Z perfect just means perfect in the usual sense. And where H was some canonical normal perfect subgroup. Usually, I guess, the maximal normal perfect subgroup. Okay. So now, the theorem. But still in an approximate form, meaning not yet saying precisely what we mean by algebraic description. But so now let's see the small connected category. And each normal subgroup, well, I should have first said R is a commutative ring. H is normal subgroup of pi 1 of the realization of C, which is R perfect. And a plus construction for the triple. I forgot to say it here explicitly, but of course, plus construction is not unique to homotopy, or need not be unique to homotopy. And then purely algebraic description of homology. Loops this plus construction coefficients in R.
With what input?
Sorry?
You give an algebraic description in terms of what?
Well, that's what I'm getting to next. But again, it will be as the homology of a chain complex having certain properties, which turn out to determine uniquely the homology of the chain complex.
So you cannot make the plus construction unique by assuming extra properties? You know,
Sorry?
assume that it's a terminal thing with that property or something like that?
No, any plus construction. I mean, the point is that if you go back to Benson's theorem, if you replace the P completion by any space which satisfies these two properties.
No, I see that it's not unique from your definition, but if you assume that it was terminal with respect to, it was a terminal, usually completion, you have to assume that the thing you get is complete, right?
Why? No.
But it's better if it's not unique. You have more.
What I'm saying is that the space itself is not unique, but it's the homology of its loop space is uniquely determined by.
So the
By
input
these
just
conditions.
comes from the category R and H.
Yes.
Yeah.
But still, I mean, I'm interested in the answer to this question as well.
Okay.
So
Maybe I don't understand the question.
Okay.
Yeah.
It's your question.
Well, I was just saying, if you assume that it was a terminal, such isomorphism, for instance, out of
Yeah.
X, is it unique? So now you exist a space which has isomorphic cohomology
Right.
with all coefficient, and you have a surjection on the fundamental group. Usually that's not, usually you would say that the completion of the localization was the
But
terminal
I'm not
object.
saying anything about completion or localization or anything.
No, but
like
plus
that.
construction, I mean, plus construction is a kind of localization, right?
Is there a way to
But-
single one out of all the spaces that you've called plus constructions? Is there a way to
Well,
single one out?
I mean, we didn't really look at that because it wasn't necessary for what we were doing. I would assume that there is a final object there, but I don't think we ever checked that.
Okay.
But, I mean, one special case to notice is the case where H is, you can always take H to be the trivial group. Because it's, well, obviously a trivial group is R perfect for any R. And you can take, in that case, if H is a trivial group, you can take the plus construction to be the original space. And so, for example, this always describes homology of groups. Okay. Just some notation. We write script B of G for the category. For the group G. So it's the category of one object. Star and then. Okay, and also we're given R and C as above by an RC module. We always talk about covariant functors. In this case. From C to okay.
But how do you compose in this?
What do you mean?
Is the composition of is T circle H, T times H, or H times T?
Oh,
Could you step
we
aside?
usually, compose from right to left, but just a minute. So G circle H equals GH. But this meaning H followed by G. It's never going to matter in what I talk about now, but yeah, that's how we do it.
Trying to see how much of a group there is.
The question is whether it's a left or right G module when C is G.
Okay. Right. No, for what I'm going to be saying today, this doesn't come up. we start off, in fact, quite a bit more generally by defining what we call an omega system. It's a four-tuple. Consisting of a pair of categories and a pair of functors where, first of all, so theta lower star left adjoint and then the composite is the identity. So technically, the natural map from this to identity B is an isomorphism. And then thirdly, theta upper star is an exact functor. Oh, I forgot to say that A and B are a B category. And so, note that since by adjointness, by point one, we have that this thing is right exact. Theta upper star is left exact. So that's automatic whenever you have, for any pair of adjoint functors. And so all this is really saying is that theta upper star sends surjections to surjections, or epimorphisms to epimorphisms. Okay. And so the, well, one of the examples that main example we're keeping in mind relative to the theorem is case where we have RC pi bond theta is a functor such that pi 1 of realization is onto kernel H, which is our perfect. And then, let's see where was all. And so theta upper star is composition with theta, and theta lower star is left conic section. Along theta. So C and so that satisfies the conditions. And which is mostly straightforward. And then the special case, Dave Benson's case, is where C is the category of another group G. And so, where we have our G moment. So that's sort of the main example we're looking at, and the main example that gives us our theorem. Okay. So in this situation where we've got an omega system for X projective object, in B, smaller category, omega resolution of X is a complex. With an augmentation. Okay, such that condition one is that, well, Pn is projective.
Yes, CN.
Sorry?
C.
Oh. Yes. So secondly, that R is exact if one applies theta star to it. And then third condition is that, well, is isomorphic to an object in the image of theta upper star. For all n. And epsilon induces an isomorphism between H0 and X itself. Or theta, oh, it is theta upper star. Okay. And now, so thing is about these, very straightforward to check that that under these hypotheses, any two omega resolutions of X are chain homotopy equivalent. And hence have the same homology. The problem with this definition is that they don't always exist. And so, for example, in the situation of example 1, we have that, let's say, state more simply, that omega resolutions exist for all projectives R prime modules if and only if H is R prime. So this is, I mean, one of the open questions is still, are there more general ways? We have one very general algebraic condition, which implies the existence of omega resolutions. And then we have a much weaker, stronger condition. Anyhow, another condition that, that implies the non-existence. And, well, okay, the fact that the two conditions are quite far apart isn't so bad, it's annoying, but the worst thing is that in this case, in this particular example that interests us the most, our general algebraic condition doesn't apply. And so we know this, we know the existence of these things only because we know that they give the homology of the loop space in this case, because we know. So I'll get more precise on this. But
That's proved by topological means rather than algorithmic.
yeah, I mean, it depends in part on whether you consider playing around with simplicial sets, topology, or algebra, but yes. Right. And in fact, yeah, it depends. Maybe let me restate the main theorem in any case, and then I can talk a little more about that. But the main theorem now says that in the situations of example 1, where H is R perfect, so let me remind you that we have CMOD mod, where H kernel if H, did I say, no, I did say H is R perfect, yeah. Then homology of loops. For any choice of plus construction, is the homology of an omega resolution of R pi. So, I'll free module. So, corollary 1 is Benson's theorem. The case where category split B of G for G finite. But notice that it also applies to BG where G is not finite, as long as, let's see, as long as the kernel is perfect, is R perfect. So Benson's theorem is this case, the category, that's the category, the ring, given P elements, and H P of T, which again, is the smallest normal subgroup of P power index. Then is a flux construction. For PG. Okay. And then corollary 2, as I already mentioned, take is a trivial group, and plus construction is just the original space. Yes. Description. Of homology in terms of resolution. And maybe mention just one more corollary, which is really a slight generalization of corollary 1. But so P prime, K, well, say R, call it R, P is a characteristic P. And pi. So take the P completion of the nerve of the category and assume it's a finite P group. Besides, that's an additional assumption. And then so homology of loops on P completion. So then we can take P completion to be the plus construction. Is homology of omega resolution. Now, okay, 2 things I want to do in the remaining time. One is to just say a little about the proof. As one can easily guess, the proof of a theorem goes by, it's a matter of just choosing the right model for the loop space, so that the chain complex of the loop space is an omega resolution. So I want to describe that briefly, what we do. And then the second thing is that I want to give one more example where we know that omega resolutions always exist, but we've not yet found any geometric description, any geometric interpretation of their homology. Okay, so meaning really just the first, you for each object in C. Okay, so we're in the situation of this theorem. For each object in C, we have a pullback diagram of simplicial sets. Where start off nerve of C, the simplicial set, mapped to, well, take the plus construction and then the singular simplicial set for the plus construction as a space. So this is map that's adjoint to the inclusion of realization of C into the plus construction. And now take the path simplicial set. With respect to some vertex, any vertex. Now pull this back to what do we call it? We just call it AC. And now take define that in just a minute. And pull this back to E new C. Okay. So so this thing is the nerve of the over category. Over C. And so basically what you can say is that this is really a diagram of C simplicial sets, functors from C to the category to simplicial sets, where we have the constant functor in the 4 positions on the right, and functor varies only with the leftmost object. But simplest just to write it down in this form. It reminds me that this was not stated quite correctly, so I'll have to fix that. But, okay, so the point is that if you look at realizations, then this thing is contractible, nerve category with final object. This thing, of course, half simplicial set contractible. So this thing the homotopy type of loops on self-construction. And so this has the right homotopy type, and then the claim is that simplicial chain complex for this simplicial set is an omega resolution. Of free omega R pi. That's all it has to check. So the point here is that, well, an omega resolution is a chain complex of RC modules, while this homology, that's an R module. So what it really should be is isomorphic homology of the omega resolution evaluated at one object, any object. Okay. So to finish, just one more example. So I'll let, I'll still call it data. The functor between small categories that's bijective on objects and surjective on morphisms. And I think that's okay. So that's enough to imply that for any ring, commutative ring R, you get an omega system. So now, go further. Need one more technical assumption. So for each object, set this to be the kernel of the map from odds of C, of the little c, to odds of D. Theta C. Okay. And I'm not assuming that it's an EI category or anything like this. So there could be endomorphisms that are not isomorphisms, but I'm looking only at the automorphisms here. And now assume for every time one has two morphisms between the same pair of objects in C, they're sent to the same morphism such that theta of phi equals theta psi. Every time one has this situation, then these two differ by an element of k lower c prime. Such that, say, phi equals alpha. So, okay. Again, composing right to left. So that's the technical assumption that one needs. And then there exists an omega resolution of each projective x in D mod if and only if KC is our perfect So this time, I mean, this is a special case of the general algebraic result that we have for the existence of omega resolutions. That general result does not apply to the situation of example one, what interests us most, but it does apply here. So we know that there always are omega resolutions, and but we've been unable to guess at any possible geometric interpretation of them as the homology of some space. Okay, that's all.
Questions?
Can you say something about the Hopf algebra structure?
Ron was looking at that for a while, but we decided to save that for later. Things got just too complicated.
What about just the ring structure?
Well, and the same thing, yeah. We did this only for the additive structure.
So how about something easier? When is this finite dimension?
That was actually, I forgot to mention that at the beginning, that was one of our original motivations for looking at this, to look for a way of identifying p-compact groups among, well, either p-local compact groups or something similar. And we worked out a whole bunch of examples of where you've got finite omega resolution, but we were unable to get any general results for that.
I mean, do you have some more examples which are sort of periodic or something like this?
Periodic in what's
In the sense that there's a bound on the dimension. R is an active field, I expect, so if it's bound on the dimension as n.
only some very concrete examples. I mean, the examples we were looking at were cases of an extension of a discrete P torus by a P prime group order prime to P. And there we were able to show that there were always finite resolutions. But in the general case, we don't even know, we couldn't even see how to begin trying to show that, or determine whether finite homology always implies a finite length resolution.
Okay.
Yeah. We would very much like to understand that better.
So Benson's original theorem also had like an interpretation as a Tor of this thing.
And there were various things, interpretation of the Tor, things in terms of minimal, well, what do you call them, projective covers,
These squeeze
and and we couldn't get any of that. Well, the projective covers, of course, don't exist in this generality, but as a Tor, we couldn't see a way of doing that. What he did seemed to be very specific, very special. So basically, yeah, the only part that we managed to duplicate was the axioms, his axioms for a squeezed resolution, which we extended to this situation.
Are there situations where you can sort of produce a standard omega resolution, where you have sort of the usual means of homological algebra?
Well, okay, this is what Dave did in his paper, using by saying, I can't repeat it, but basically at certain stages took projective covers, and so that gave a canonical resolution. But in this generality, there are no projective covers, and, so that we couldn't see a way of doing it canonically. I can't remember, did we, were there cases we constructed explicit resolutions for certain cases, but there was no, they were clear, we could see that they were minimal length comparing homology, but minimal numbers of generators.
Anyone else?
Think about it.